Hi, everyone. Welcome to our second lecture bite of the week for week 9. This week, we're talking all about exoplanets, and this lecture bite is going to cover the exoplanet revolution. So how we got from the first detections of exoplanets that we covered last time to how we got to the massive population of exoplanets that we learned about now, and some of the things that we've picked up along the way. So, as a reminder, last time we talked about the technological advancements and the methods that were used to find the very first planets outside of our solar system. And what we learned is that we used the radial velocity method to find planets by very precisely measuring Doppler shifts, measuring the speeds at which stars are moving back and forth. We never see the planets, but we see their gravitational influence on the star, and we can learn about them through that. So the very first planet that set off the field, the one that was widely considered to be the one that convinced people that there were really planets outside of our solar system, was 51 Pegasi b. But in the last 30 years, the number of planets we've discovered has grown exponentially. So this plot is showing the number of exoplanets that we knew about over time. So you can't even see these early discoveries here from 1988 and 1995. But shortly after that, the rate of discovery started picking up, and we started finding more and more of these planets. And I'm going to go through the history of how we were able to do this and how we were able to make these massive leaps in this lecture bite today. So how did we get here? When in 1995, 51 Pegasi b was discovered, the precision of our measurements was just barely sufficient to detect Jupiter-sized planets. So if you recall, Jupiter around our sun causes a signal, causes the sun to move back and forth at about 12 meters per second, or about 27 miles per hour, the speed of a slowly driving car, perhaps going through a school zone or something. But the other planets have even smaller amplitudes and are even harder to detect. So if we wanted to find smaller planets and more planets, our technology would have to keep improving even beyond what was necessary to find the very first planets outside of the solar system. And the more we improve, the more challenging this becomes. To put this into context, the way we measure radial velocities now is we take our light and we spread it out into different colors, into different wavelengths, like a spectrum. We've covered this many times in this class before. You can see the spectrum looks kind of like this. You get these streaks of color, streaks of light with all different colors, and you go from red up here to blue down here. And all along this horizontal direction are different wavelengths as well. These light is then projected onto a chip, a silicon chip called a CCD, a charge coupled device. This is the kind of chip that's inside of your digital cameras and your phones that we use to take pictures of ourselves all the time. But we don't have to be nearly as precise with our cell phones as astronomers do when they're trying to measure shifts of spectral lines by very small planets. So for example, if you're trying to measure the shift of a spectral line, say measure the wavelength of the center of a line as a planet is orbiting and pulling it back and forth, that line is only moving by a few silicon atoms on this detector, a few dozen perhaps. These are incredibly tiny shifts, and it makes it really difficult to do this. So a lot of our technology over the last couple of decades has improved because we've become more careful and more fastidious in how we make our spectrographs and prevent them from moving around at all. Because any movement, even movement of a couple of atoms shifting upwards or downwards, is enough to throw off our results. But we've been able to do this. And here's an example showing what we've been able to achieve. So you can see here over time, this is the year 2001, this is the year 2014, how the scatter in our measurements of the speed of the star have improved. Back in 2001, on a given day, we were lucky if we could nail the speed of that star, if we could measure the speed of that star to within about 20 meters per second of its true value. But as we got new technology and we built new devices to do this, our scatter improved, our precision improved. And finally, we were able to start measuring them to the point where you can barely see the errors at all on this diagram, to where we're always measuring the velocity right on the dot of that line, which means that over time, we've been able to find smaller and smaller planets as well. One of the pioneering instruments, one of the pioneering spectrographs that helped us improve our ability to find these small planets is called HARPS. HARPS stands for the High Accuracy Radial Velocity Planet Searcher. And one of HARP's innovations was that it was vacuum sealed. If there's no air inside the spectrograph, then you can't have changes in air pressure or changes in temperature cause any motion of the device. So nothing at all is moving. It's also highly stabilized so that when earthquakes hit, or if someone jumps too high on the next floor over, that doesn't cause the tiny shifts that would throw off our measurements and cause us to be able to miss planets that were small. And these innovations really paid off. So here's a comparison of the kind of data we were able to collect in the 1990s. Here's the Discovery radial velocity observations of 51 Pegasi b again. And notice this y-axis here. The scatter around these observations is something like 10 meters per second. You can never really try to get your observation to be better than about the distance between one of these two tick marks here. And then compare that over here to observations from HARPS just a decade later. Now this entire axis range is about 20 times smaller. Instead of going from 100 meters per second to negative 100 meters per second, we're measuring velocities all between 5 and negative 5 meters per second. And the scatter about these solutions is less than 1 meter per second. So less than the walking speed of a person. So these improvements have greatly improved our sensitivity to small planets. Whereas here, we could only find Jupiter mass objects. Here, we're finding things smaller than the mass of Neptune. And our improvements have continued. These are observations of the nearest star to the sun, Proxima Centauri. The orange and red observations are from the previous generation of spectrographs. I believe orange is actually from HARPS. These green observations here, these teal observations, are from a new instrument, kind of the state of the art today, called Espresso. And you can see that there's an impressive improvement in the scatter in those observations. So Espresso is now routinely measuring radial velocities to precisions better than 1 meter per second. We're starting to close in on the territory of box turtles and how fast those objects can, or those creatures can walk, in terms of being able to measure the speeds of stars hundreds of millions of miles away to these incredibly precise values. So this is one of the reasons and one of the ways in which we were able to improve our knowledge of exoplanets. As our technology improved, we kept finding smaller and smaller planets and just kept discovering more and more of them, even around the same stars that we used to observe. It's just now we finally had the sensitivity, we finally had the precision needed to discover these tiny signals. And over time, I'm showing here the publication date of exoplanets discovered with radial velocities with this Doppler technique. Over time, our improvements in precision have led us to find smaller and smaller planets, to the point where now we're starting to hit planets that are roughly about the same mass as our own Earth. So the radial velocity method was the most important discovery method in the early years, and it really dominated everything that was going on from the 1980s until the mid-2000s. But the next thing I'm going to talk about picked up the slack from there and has continued to expand our knowledge even faster than before. And that is a new method for finding exoplanets called the transit method. So transits are actually quite conceptually simple. All you have to have is a planet whose orbit is lined up just perfectly between its star and our telescopes, so that it seems to go in between our telescope and the star, cast its shadow on our telescope, and we measure that as a slight dimming in the brightness of the star. So every time this planet goes around, we can see that the brightness time series over here on the left gives a small dip. Yeah, every time the planet goes in front, we see this small dip in brightness. And if we see this happening repeatedly, we can infer the presence of a planet. The very first planets that were discovered to transit, as we say, to have this favorable alignment so that their orbit takes them right between the telescope that we're observing with and the star, was already discovered with radial velocities. So this planet is called HD 209458b. It was discovered with Doppler observations, like most of the planets were back then. This was in the year 2000. And then based on these observations, a team of scientists knew that if they went and looked for dips in brightness, when they should do that. And this was actually done in the parking lot of a scientific research center in Colorado using a very small telescope that was not even, astronomical grade. It was just a small telescope with a camera attached. And that ended up being one of the biggest discoveries in the field of exoplanets. So this discovery, the discovery of a transit of HD 209458b, really changed the landscape for exoplanets. Because for the first time, we actually measured a true mass of an exoplanet. Because we know that the orbit has to be aligned like this, because the planet goes in between the star and us, we know that we can't be misaligned, and therefore we know that the mass can't be actually larger than what we measure. So instead of measuring a minimum mass with the radial velocity observations, we measured a true mass of this planet. Transits also tell us something very important about the size of the star. Not how much mass it has, not how much it weighs or how much heft it has, but physically how large it is. We observe transits to block some fraction of the star's light. The bigger the planet, the bigger the shadow it can cast, and the more light appears to be blocked from our point of view. So transits can help us infer the size of the planet that's orbiting. If you combine the size of the planet and the mass that we measure from radial velocities, you can measure the density of the planet, and you can figure out just how it compares to the planets in our own solar system. So for the first time with HD 209458b, we were able to say this planet is bigger than Jupiter, but it's lower mass, so its density is lower. And that helped us understand what the diversity of planets in our galaxy can be like. They don't all have to be exactly like Jupiter. There is some scatter. Some planets can be slightly bigger, and some planets can be slightly puffier. The real revolution with transits, though, came not when we were searching for transits of planets that we already knew existed, but when we started looking for planets by their transits first. So the way this works is you set up a camera that can observe many, many stars all at once. And for each of these stars, you measure the brightness over time. So you get a brightness measurement, kind of these time series is ticking off over time. And in all of these stars simultaneously, you look for any dips in brightness that might be there and that might be repeating. This is how a large number of exoplanets have been discovered so far. The technology needed to do this is actually quite simple. So here's one of the successful planet hunters that have been used to find planets using this method. It's called the Kilodegree Extremely Little Telescope. Kilodegree because it surveys an area of sky 1,000 degrees square. So, 30 degrees on one side of its field of view and 30 degrees on another side. So a relatively large swath of the sky. And this little telescope, and I say telescope almost in air quotes, was able to find 26 planets. The reason I put the telescope in air quotes is that this telescope is actually just a camera lens. In fact, it's this camera lens. It is a fairly nice camera lens, but nonetheless, it's just an off-the-shelf component that was retrofit into being used for astronomical discoveries. So starting in the mid-2000s, planets discovered by the transit method started to become more popular. But the thing that really caused transits to take off, literally, was the was the advent of space-based observations. So I've said this a few times already this week, which is that Earth's atmosphere is really hard to deal with if you're trying to make precise observations. The stars that we observe from the ground through our atmosphere bounce around due to these turbulent pockets of air that have different temperatures and different pressures. And this makes it hard to tell exactly where the star is. It also makes it hard to tell exactly how bright the star is. So this limitation has basically made it so that from the ground, we can really only find planets about the size of Jupiter. Anything smaller, and we just can't make brightness measurements precisely enough to do that. But we can do better if we go to space. So here's an example of what you can do if you go to space. These are observations of a planet called HD 189733b. These observations were taken from the ground, and you can see that there's this relatively large scatter in the brightness measurements. We can't measure the brightness measurements super precisely from the ground because the observations, the stars bouncing around and changing around how bright it appears to be and where it appears to be. But if we go to space and use something like the Hubble Space Telescope, we can greatly improve the precision of these measurements, and we can make these extremely precise brightness measurements that we can use to find smaller and smaller planets. The big game changer here was the launch of the Kepler Space Telescope in 2009. Kepler was NASA's first telescope in space that was specifically designed to observe exoplanets, and it was phenomenally successful. Kepler was a 1-meter telescope, so relatively big, about 3 feet across meter diameter, and a mirror 3 feet across in diameter, that pointed at the same part of the sky for long periods of time. It observed hundreds of thousands of stars, and it carefully measured their brightnesses every 30 minutes. And if the stars dimmed in brightness, we were able to infer that there was a planet orbiting that star. Kepler discovered most of the planets that we know about today, and that's not even an exaggeration. If you look up how many planets were discovered by Kepler and how many planets we know of total, it's something like 60 to 70% of the planets we know of, period, were discovered by this telescope. It's impossible to overstate just how revolutionary this telescope was to our understanding of planets in our galaxy. And all of this happened in the last decade. It was 2009 when this telescope launched, and only in 2010, 2011 did the first discoveries and the first data start coming down. So exoplanets is a rapidly moving field, and we're making incredible strides in our understanding of planets throughout our galaxy right now. It's moving so fast that it's almost impossible to keep up with textbooks. So here's the impact of Kepler. Kepler launched here in 2009. Right after its launch, it took a little while for it to get going, and that was because the data were not quite processed yet. They weren't released to the public. But as soon as that happened, the data started going public right around here in 2012. There were these just tremendous jumps in our knowledge of planets. The overall rate of discovery increased, and then there were these big jumps here and here. And those two big jumps all came from individual papers. So there was a paper in 2014 which discovered something like 500 planets all at once. And there was a paper in 2016 that discovered about 800 planets all at once. And these discoveries are still continuing. People are still using Kepler data today, and we're still finding more and more planets. And Kepler is a big reason why, if we look up how all of the planets that we know about were discovered, they're dominated by planets discovered by the transit method. This is all thanks to Kepler. So now that we've gone over how we've begun to find planets and how we've begun to begin our census of planets in our nearby galaxy, I wanted to go through a couple of the most important things that we've learned about planets in the last couple of decades. The first one, the most important takeaway, is that planets are common. There are more planets in our galaxy than there are stars. Planets are the rule, not the exception. They're a natural consequence of the formation of stars. Before a couple of decades ago, we didn't know this to be true. We didn't know if it was unusual for a star to have a planetary system like our own. Now we know that planetary systems are a dime a dozen. They're everywhere. Number two, small planets are more common than large planets. Earths are much more common than Jupiter's. This kind of makes sense, right? It's hard to have enough material formed together to make a really big planet. But you could imagine that if you fail doing that, you end up with a small planet. And this seems to bear out. So these two graphs are showing the results of two major surveys. This one with HARPS using the radial velocity method, and this one with Kepler using the transit method. And both of them find basically the same thing, which is that when you look at this regime of here, giant planets, massive like Jupiter, there are relatively few such planets. But when you start looking down here at things that are roughly the mass of Neptune or lower, all the way down to the mass of Earth, they become much, much more common. Same thing over here from Kepler. Small planets about the size of Earth are relatively common. Above the size of Neptune, right around 4 times the size of Earth, planets become much, much less common. Small planets like our Earth, the ones that are potentially rocky, are the rule, not the exception. And finally, the planets outside of our solar system are far more diverse and far more amazing than we could have imagined just by looking at the planets in our solar system. You recall that for hundreds of years, astronomers only were able to look at the planets in our solar system. And we looked for patterns. We inspected those 7, 8, 9 planets to death, depending on how you want to define it, and when you were observing. And we learned so much from them. But over the last 30 years, we found that our knowledge is just woefully incomplete from our solar system alone. If you want to understand planets, you have to look outside of our solar system and look at the entire group in our galaxy. So here's an example. Recall that in our solar system, all of the planets orbit in the same direction. All of them orbit in the same direction as the sun's spin. This was causing us to believe that planets seem to orbit all in the same way, and they were formed in a disk. But in exoplanet systems, we found that this isn't necessarily true. Exoplanets aren't necessarily on orbits that are aligned with their stellar spin. Sometimes they're in orbits that are aligned at some weird angle, and in other cases, they go opposite of their solar spin, their stellar spin. How could these planets be this way? We generally think that planets do form in disks. We see disks outside of our solar system. We think they must be where the planets form. So what could have happened to the planets in the meantime between their formation in a disk to where we see them now, so that they seem to be going the wrong direction? We think that the intervening years, the early evolution of planets, is a lot more dramatic and a lot more eventful than we used to think based on our solar system alone. We, in our solar system, know of 4 rocky planets and 4 gas giant planets. The largest of the rocky planets is Earth. The smallest of the gas giant planets are Uranus and Neptune. They're about the same size. And there's really nothing in between. There are no planets twice the size of Earth or 3 times the size of Earth. But it turns out that in our galaxy, planets that are in between the size of Earth and Neptune are some of the most common planets out there. What are they? Are they more like Earth? Are they super Earths? Or are they like scaled down versions of Neptune or mini Neptunes? Are they rocky? Are they good places for people like us to live? Or are they gas giants shrouded by thick atmospheres that would make them unhospitable for life as we know it? We just don't know. And this is one of the big things we want to keep understanding. There are some planets that have such extreme physical parameters, it doesn't even seem possible. So for example, consider the case of HIP 41378F. This planet is 9 times the size of Earth. If you look over here, the other planets that are around this size are like Saturn, Jupiter. These are really big planets and they have a lot of mass in our own solar system. But this planet has a mass of only 12 Earth masses, which means that it's less massive than Neptune and Uranus. Therefore, the density of this planet is extremely low. It's almost like a planet made of cotton candy. It has almost the same density as cotton candy. How could a planet be like this? How could a planet be so huge physically and yet so lightweight? It just kind of boggles the mind. And finally, in our solar system, I don't think we talked about this yet, but the planets seem to orbit in orbits that are mostly circular. Some of them have slight stretching to make them look like ellipses or to be egg-shaped essentially. But for the most part, they look pretty circular. And here's an example of this. This is the orbit of Mercury. Looks like a circle to me, even though this one is actually the most uncircular of all the planets. Here's Venus, also looks like a circle. Here's Earth, also looks like a circle. This is not necessarily true of exoplanets. Some of them have extreme orbits that are extremely stretched out, like this planet here. This is called HD 80606b, and its orbit is so extreme that at its furthest extent from the star, it almost reaches the location of Earth, if Earth were in that same solar system. But it falls down every 84 days or so and just grazes by its sun, just barely escaping being inside of the sun. It gets heated up as it does that. It gets really, really hot as it passes by, and then it cools down as it journeys away every 84 days or so. These planets have just such extraordinarily weird orbits. We couldn't have imagined that this was something that could happen looking at our solar system alone.